Okay, so last time we were talking about different ways to measure performance in binary classification, and we said that the situation is much more complicated than it is with regression because there's different kinds of error. There's false positives and false negatives. And so the maybe the most basic way of measuring performance, which is just that the estimated class equals a true class, kind of hides the difference between those two types of errors. And so in some applications, we would like to use some metrics that more carefully distinguish between false positives and false negatives, such as precision or recall, or their harmonic mean, F1 score, or in medicine, we have sensitivity and specificity. And this confusion matrix is, as we'll see, this is something that's often presented to visualize the performance, like in a demo or a notebook, a Jupyter notebook. Okay, and then we saw that in sklearn, it's very easy to compute these different metrics because you can just choose the scores. Instead of mean squared error or negative mean squared error, you could choose any of these when you're doing classification. Okay, so now we're going to switch gears a little bit and think back to how we formulated linear classification. We said it was a two-step procedure where we first compute a score z, and then we threshold that score. So you said to set y hat equals 1 when z is greater or equal to 0, right? Because when z equals 0, that is sort of the boundary between predicting class 1 versus class 1 versus class 0. At least that's what we said to do. And so that's the typical, what we call hard decision. Okay. So there's another approach which is a bit more informative, and it is to use what's called a soft decision, which is not to report an integer guess, but actually to report the probability y equals 1 given z itself. So that's going to be a real number between 0 and 1. So those are called soft decisions. These hard decisions that's the y hat. And a way we can generalize the choice of the hard decision, we said always set it when z is greater or equal to 0. So basically this is equivalent to when the probability of y equals 1 given z is greater or equal to 1/2, right? Z being greater than 0 means probability of y given z is greater than 1/2. So that is the standard option, but we can be more general. We can instead, so this is a generalization of this. We can, instead of choosing 1/2, which is what we're using over here, we can use some other number t, and we can choose t somewhere between 0 and 1. So the standard choice, when t is 1/2, that is the thing you want to do if you care about accuracy. That's the best choice. But if you care about precision and recall, and maybe you care more about precision than recall, you want some trade-off, then other choices of t could be better. So, if you're designing, let's say, a COVID test, and the health department or whoever says we need to somehow balance the false positives and the false negatives, and we're going to do that by specifying your precision must be at least this good and your recall must be at least this good. And so now, by choosing T, you can kind of trade. Here's the plot. This is the threshold T. This is the standard choice of 0.5, which would give you, for this experiment, that would give you some particular precision and recalls. I don't think they're necessarily always the same, but they are in this experiment. But if you want to increase T, you would notice that your precision increases while your recall decreases. So, if someone says these are the requirements for this design, then you could choose T to best fit those requirements. Okay, so what we're doing here is we're revisiting our choice of thresholding Z at 0, or equivalently the probability at 1/2, with some other threshold T on the probability. Is this making sense? Okay. This is not a great slide. I actually revised the slide, and I just uploaded a new version to the course repository. But anyway, so this is the main idea. Similarly, if you choose T different than 0.5, you can trade specificity, larger T, more specificity, but less sensitivity. So here too, you can kind of balance those objectives by choosing a different T. Okay, any questions on this? Okay, another way this manifests, especially in electrical engineering, it's very common, like in radar, it's a very classical thing to talk about the receiver operating characteristic. And this is the plot of the true positive rate versus the false positive rate as a function of T. Okay, so here's the plot here, and you can see we're plotting true positive rate, false positive rate, and as you change T, from what I remember, it is this way, larger T. As you change T, where you are on this curve changes. So, and just to remind you, the true positive rate is a probability that your guess of y equals 1 is correct, and the false positive rate is that your guess of y equals 1 is incorrect. Okay, so as we change the threshold, we can move where we are on this curve. And here again, your boss might say, we need a detector or a classifier that has true positive rate at least this, or a false positive rate at most that, and so now you can choose a threshold to change that. Okay. Okay. So kind of similar. Is that making sense? Kind of similar to what we had on the last page. It's sort of a trade-off. Now, the thing about this is that sometimes you don't exactly know how you want to trade off between these at the time that you're designing, training your system. You might say, well, I generally want my true positive rate to be as large as possible and my false positive rate to be as small as possible. They're conflicting, so it's impossible to do both perfectly. But I don't exactly want my whole system designed to depend on a very specific choice of these two. I want it to kind of work well over a range. And so you could maybe do something like have it, F1 score is kind of measuring, some overall precision and recall. But even here, these things are going to depend on a particular choice of t, right? Because it's only when you choose t that you know exactly what your precision and recall are. So you might say, I want to design a system that works well kind of over a range of t. And so that is the idea behind what's called area under the curve, AUC. And there's different curves to measure that area under, but so what I'm showing you here is area under the ROC curve, the ROC curve. And basically what that means is, here's your ROC curve. You can see that this is 1 here from on the vertical axis from 0 to 1, on the horizontal axis from 0 to 1. And the area under the curve, literally, you just measure this area. And you can see that the best possible system would have a ROC curve that looks like this. So this is like the ideal system. A practical system is going to cut this corner somehow. The harder the problem or the worse the system, the more it gets cut off. And so the AUC is just sort of like an overall measure of how well the system works over all different t, all different possible thresholds. Okay, so this is a threshold independent metric, which is nice because it doesn't require you to choose a threshold in order to talk about how well you're doing. So this is a very popular thing. You'll see people talk about AUC a lot. It's kind of something that's a bit more robust than probability of error. And there's different ways, like I said, different curves you can measure under. You could also do it under like a precision recall curve. You could do area under that curve. Okay, so very commonly used in machine learning. Okay, so I think that's all I wanted to say about binary classification. Any questions about how we measure performance in binary? Okay, now let's move on to multi-class. This is a little bit more complicated, or at least it could be more complicated, so I'll describe to you what people actually do. So in multi-class classification, we have a confusion matrix that looks like this. So here we have all the possible true labels, all the possible predictions. And so there's many different ways that we can be correct. So this is one way we can be correct. If the truth is y equals 1, we guess y hat is 1. That's one way of being correct. Another way of being correct, if the truth is 2, and so on and so on. So we have like k different ways of being correct. And now you can see we have a whole bunch of different ways of being incorrect. It used to be 2 in binary. Now it ends up being k times k minus 1. So tons of different ways of being incorrect. So that's obviously can be overwhelming. So one of the things that people often do in printing these or interpreting these confusion matrices is they normalize the rows so that they sum to 1. So if every row sums to 1, then when you look at those numbers, they can be interpreted as the probability that your guess equals L, which is going to be the row index, the column index, given y equals k, which would be the row. Okay, so this would be, k would be coming down this way, and L be going that way. Okay, so that's kind of a standard thing. If you don't normalize it, then these are just different counts, and it's really hard to make sense of what's going on. They're just integers. Okay, and then we talked about these different diagonal terms. Those guys are going to be what we'll call per class accuracy. Per class accuracy is like the probability you guessed correct for one of the classes. Okay, so the first thing to notice, we'll come back to this in a moment, is that the overall accuracy, which we talked about before, that's this one, can be computed by averaging the per class accuracies. Okay, so the reason or the way you do this is you just use this kind of, I don't know, almost like an identity from probability, which is just a way to take your conditionals and turn them back into the marginal. So when we look at this, we see that you want to do a weighted average of these guys, and the weights have to do with how often that class exists. So we'll talk about the imbalanced case where maybe one of your classes is extremely rare, so that number would be very small. And so that would mean that the per class accuracy for that class would have a very small effect on the overall accuracy. Okay, but we'll talk about that in a moment. Okay, so given that we have like all these different ways to do things correctly and all these different ways to make errors, one of the common things to do is to compute binary metrics, so all the ones we talked about, for each class using these k versus rest metrics. So the idea is sort of like this. So let's say we want to talk about class 1 versus the rest. So what we do is we sort of like partition the table, almost like this way, and we group all these together, all those other things together, and say this is not 1, this is 1. And then over on the correct side, this is 1, this is not 1. So then we basically we kind of sum all these together, sum all those together, sum all these together, and that takes us to a nice 2 by 2 table where we have y hat equals k, y hat not equals k, y equals k, y not equals k. And so now that we have boiled it down to this 2 by 2 case, we can do all the stuff we talked about before, but it becomes class specific. Okay, now you might say, all right, that's a lot of information. What if I have 10 classes? Now I have like 10 different precisions, 10 different recalls, and so on. So what people then do is they combine them using different forms of averaging. So, and in particular, there's 3 forms. There's macro averaging, micro averaging, and weighted averaging. So let's take a look at macro. So these TPs are the true positives for this K versus rest. So you take these numbers in here, and in this case, you just average without any weights over, this is for precision. This is just an example for precision. You just average the 1 versus rest precisions. That's called macro. Micro is like you do the averaging separately in the numerator denominator, and then weighted is kind of like the macro, except now you plug in the probability of y being in that class. Okay, so we got basically, you compute these little 2 by 2 tables for all your classes, and then you combine them in one of several ways. So there's a bunch, of details here, and you can click on this link if you'd like to know more, if this is important for your research or something. But just sort of showing you at a high level, these are the things people do to measure performance in multi-class classification. So there's a lot of choices. You have to just make a decision and maybe choose wisely for your application. Okay, so that's multi-class. Any questions on that? Okay, so now let's talk about something that happens often in practice, and if you don't handle it well, you get in big trouble, and that is imbalanced class labels. So the idea is you have a case where some classes have many fewer samples than others. So let me just give you an example. If we are testing for a disease like COVID or something, and let's say our population that we're testing, maybe only 1 out of every 1,000 people we expect to have the test. So 1 out of 1,000 on average is sick, 999 out of 1,000 are healthy on average, right? So if you think about that, and if you care, or if you think about what happens to your total accuracy, and let's say you design a test. You say, my goal is to come up with this test of high total accuracy. Well, if you think about it, you could come up with a test that no matter what says everybody is healthy. And that test will be correct 999 times out of every 1,000, right? But your test is trivial. Your test is stupid. So this shows that high total accuracy, again, is even in the binary case, is something that is not necessarily a good idea. And it becomes especially problematic in this imbalanced class scenario. And this equation shows us the problem. So, maybe for our majority class, always guessing healthy is obviously going to be the right thing to do. And so that's going to be, 1 or near 1. And now we're going to multiply that by 0.999. So that's going to add a lot to this. And now for the minority class, we're always going to be wrong because we're just ignoring them, saying that they're healthy no matter what. And they only add 0.001. And so that's how we're getting a high overall accuracy, even though for the minority class, this per class accuracy is terrible, 0. So that's the issue. So one way to get around this is instead of trying to optimize this, you use balanced accuracy. So what we've done here is we have removed this term. So we've basically replaced that with 1 over k. And so if you say this is the criteria, now you can say, okay, if I have 2 classes, healthy and sick, I'm going to just take 0.5 times the healthy probability and 0.5 times the sick probability. And that's better than this, which is 990, we're weighting the healthy ones 999 over 1,000. Okay, so this is one approach. The way or the place you would use balanced accuracy is not in the training exactly, it's in the hyperparameter selection. So if you think back to logistic regression, when we formulated logistic regression, we never talked about a goal such as maximizing accuracy or precision or recall. We just said we have this logistic model and we want to do maximum likelihood, and boom, we get some weights. Right? The place where this matters is when you have hyperparameters and you want to do cross-validation. You want to say, how well is this working on my test set, or I want to choose my ridge or my lasso parameter. At that point, you have to say, what is my criteria? It's not mean squared error, because we're doing classification. So is it accuracy? Is it precision? Is it recall? Is it F1? And that's where you can use something like balanced accuracy. Okay. All right, any questions on, I'll write this for cross-val. Any questions on this? Okay, now let's think about the training. There is something we can do actually during training. When we train versus via cross-entropy loss, or really, all the losses we've talked about, we're always averaging or summing over the samples, right? So these are the samples I in our data set, and we're just summing over the loss for those samples. But if you think about it, if 0.999 ratio of my samples are one way and then 0.001 are different, when I average the loss this way, it's not really taking into account those minority samples very well. So what you can do during training is you can use something called class weight equals balanced as one of those parameters in, for example, logistic regression. And what it will do is it will basically weight the terms in here in a different way. So it will weight them according to or kind of inverse weight them according to their prevalence. Okay, so that's the second thing you can do. 1, 2, and then any questions on that? Okay, one last thing you can do. When you do k-fold cross-validation, if you think about it, if you have a rare class, it could be that the samples for that rare class are going to be missing from a lot of your folds because your folds are just random and maybe they're not tons of samples in the fold. So maybe the minority class is just missing from some folds, and that means that the error you measure in those folds might be misrepresenting what you really care about. So there's a version of k-fold or a parameter you can use called stratified, and that when you do that, when scikit-learn chooses the indices for the folds, it makes sure that they all have the same class balance. That it's not like some folds have way more or way less minority samples than other folds. Okay, so these are the three main things you do if you want to handle an imbalanced class well. And sometimes the final project, you get a data set with imbalanced classes, and the people who do this stuff have like way better performance than the people who don't realize or forget that we talked about this. Okay, so this is a big and important thing in machine learning. Not always. Sometimes you have very balanced data, but sometimes you don't. Okay, good. Any questions on imbalanced classes? Okay, so that takes us to the end of this unit. And so we can start our next unit on optimization and gradient descent. And our motivation basically builds on what we just saw in our classification unit, where we said that to train our logistic regression model, we have to solve a challenging optimization problem, something that we don't know how to do. We know that scikit-learn can do it, but maybe this is good for us to study a little bit more about it as well. So the problem that we saw we want to solve looks like this, where we have our cross-entropy, in this case binary cross-entropy loss. We have a sum over our training samples of the natural log of 1 plus e to the power zi minus yi times zi. And this is the version when we have labels in 0, 1. And here, z of I is going to be the vector 1 xi transpose times the vector w. And so what I've done, just to make the notation a little bit easier, is rather than giving the bias a different symbol b from the weights w, I just defined the 0th weight as the bias term, kind of like what we did back in our linear regression, and then we augment the features with the one valued feature that will multiply the first element in our weight vector. And now we can just optimize over a single parameter rather than having to write minimize over b and w. Okay, so this is what we saw in the last unit. Okay, so the big challenge is we notice that this is a lot more complicated than linear regression. We cannot just set the derivatives to 0 and come up with an analytical expression. We know that there's ways to do it. So scikit-learn gives us this logistic regression method. It actually has a whole bunch of different algorithms inside it. Now we'd like to understand a little bit about what's happening, like how those algorithms are working. And this is going to be really important as we move on to neural networks to understand the challenges in training them. So that's the motivation for us. We don't really have a data set of real data or anything in this unit. It's just, this is our goal. Okay, any questions? Okay, so we're going to sort of start at the beginning. This is something we kind of alluded to way back in Unit 2, gradients and optimization, but now we're going to zoom in a little bit more and more refined grain. So okay, so our goal in this unit is to solve one of these minimization problems where we have some cost or loss. These are different words. And usually the symbol is given J in the literature for a cost or a loss. And so this is going to be a function that takes us from our tunable parameters to a real number. So this is a real number. And what we said back in Unit 2 is we can exploit the gradient, at least sometimes. So let's be a little bit more precise. So, okay, so what is the gradient? And we'll come back to proving this in just maybe today, maybe next lecture. But the gradient is basically telling us the direction of maximum increase at the point W of this J, and the slope, how much it is increasing. So we have this picture here where we have these little arrows. The length of their arrow represents the magnitude of the gradient, and the direction of the arrow represents the orientation of the gradient. So in this case, for example, this would be like W0 is one parameter, W1 is the other parameter, and we're trying to maybe optimize the pair of those two things. We're trying to find the point here at which this is, let's say, usually we formulate it so that we minimize. In some cases, we can also write it as maximization, like maximum likelihood, but often it's written as a minimization problem. So let me ask, let's see, is Vedant Karthik here? Okay, what about William Huang? What about Paul Gable? Okay, Paul. So given this picture and given what I just said about the gradient, what are these two things showing us in words?
He's showing, like, if you were to take an integral, like, what level would it be at?
Yeah, okay, you're right. It's so we call these cost contours. So it's kind of like the cost is the same everywhere on that ring. But more specifically, when we're looking at this function J, is there a minimum or a maximum or both or neither?
One's the minimum.
Which is the minimum?
Minimum is the right because they're going in.
Okay, but so this is what I wanted to emphasize, the direction of maximum increase. So when those arrows are pointing in, remember they're telling you where uphill is. So what does that tell us?
It tells us the direction of the maximum is in.
Yeah, right, exactly. So these guys, they're always, arrows are pointing uphill. So this is the top. This is the peak right here. And what about this? What is this?
Minimal.
Exactly. This is like a trough, a depression. Okay, so that's what the gradient is telling us basically. And so something that's important is the gradient may not always exist. We hope it does, but there are cases where it doesn't. For example, in our lasso formulation, there was the L1, right? And if you kind of visualize L1 along one parameter, it looks like a V. And at the bottom there, the gradient doesn't exist, right? It's a sharp edge. It's not differentiable at the bottom. So this kind of gradient style optimization does not always apply to everything in machine learning. It does not apply to lasso, for example. But it does work with ridge. It works with least squares. It works with logistic regression. Works with pretty much everything else we've seen except for lasso so far. But I just kind of want to point this out. This gradient exists if it's differentiable. And we will assume throughout most of this unit that it is, unless I tell you otherwise. And then finally, the important thing or one of the important things for us is at the minimizer, the gradient is 0, right? So here, right, at that minimum, if you plotted an arrow there, it would have 0 length. And so that is something we can try to exploit. What is the gradient over here? Anybody? At the peak.
Also 0?
It's also 0, right? So this is something that we also have to contend with too. It's like setting the gradient to 0 is not quite enough. You really need that the gradient is 0 and that there's a curvature which tells you you're at a minimum rather than a maximum. We'll talk about this a little bit more in a moment. Okay, so that's the gradient, super important concept for this unit. And we'll show how the gradient can also be used to linearly approximate a function in a few slides. Okay, any questions about gradients? Yes?
Would the same, was similar concern with the gradient being 0 also apply for like local minima?
Yes. Yeah, there's, yeah, we'll talk a lot about this later, but there's basically three places the gradient can go to 0. It can go to 0 at any minimum, at any maximum, and at things called saddle points, where okay, this doesn't have one, but a saddle point is where, like, in one direction you look, it has positive curvature, but it's like you're at the bottom, and in the other direction, it has negative curvature. So it's just like a saddle on a horse. Like a saddle on a horse, or like a Pringles potato chip, you know? So it's like, there's that point, it has 0 gradient, but it's neither a minimum nor a maximum. It's kind of both and neither. Yeah, so those are the 3 places we can have that gradient going to 0. Yes?
So in the past, we used the RSS because that minimum is the global minimum, right?
Exactly. So the nice thing about the RSS or sample MSE is that if you would plot it, it looks pretty much just like this side everywhere. So there's only one minima. It's unique. It's the global minima. There's no issues with convergence, really. You know, we can just try to find that 0 minimum location. I guess technically there is one issue. If you have more features than samples, what happens is there's this one or several directions where there's no curvature at all. It doesn't curve up or down. So it's kind of like this. And so actually the minimum is not unique. You know, RSS is minimized everywhere along here. Now you might say, okay, are they all equally good? Well, not exactly, because these ones out here might have very large beta parameters. Maybe, you know, this one is close to 0 and then here large again. And what we saw is there's an overfitting problem. As those parameters get larger, they amplify noise. And so that is sort of an issue. So when you have these correlated features like in ridge regression, what's happening there is that your cost function, even though it is quadratic, is very stretched out. And it's you know, due to like training noise and stuff, you know, you end up somewhere along here that is not where you want to be. And so when you add that L2 regularization, it kind of forces the contours to be closer to circular. So that's another situation we encounter. Okay, great. Any other questions? Okay, good. So let's talk about the gradient mathematically. So again, this function j is always scalar valued. If it wasn't scalar valued, that would be like saying, I have 2 different objectives. I want to do this and I want to do that. And now it's not really clear what you want to do. So we only have one objective, and this j measures like how good we're doing it. We want j to be as small as possible. So it's a cost. It's like we want minimum cost. Okay, so if the thing we are optimizing, like in logistic regression, in binary logistic regression, is just a vector of weights, then the gradient is defined as the partial derivative of j with respect to the first weight. So, or how do I want to write this? So here, for this page, we will assume that we start counting at 1. So we're going to take it with respect to the first, and then the second element is dj dw2, and then the last element is dj dwd. Okay. Now, we have seen situations where the thing we're optimizing is actually a matrix. So we saw this with multinomial logistic regression or regression with multiple targets. We actually have a matrix we're optimizing where every column contains the prediction parameters for a given class or for a given target. So in this case, the gradient is also a matrix. And once again, it has partial derivatives. So it's going to be dj dw11, dj dw, how do I want to write this? Sorry, we're gonna take a shortcut and go all the way to the end. dj dw 1k. So we will assume that this matrix W has k different columns. And then if we go this way, we have dj dw d1, and then if we go this way, have dw dk. Okay. So the key thing to remember, if we were wondering like what is the shape of my gradient, it's always has exactly the same dimensions as your input. Whatever you're optimizing, the gradient is just exactly the same dimension in terms of dimensions. Okay. Any questions about how the gradient is defined? Okay. If you have a tensor, which is like a three-way array, then your gradient will be three-way, same size. Okay, so let's just do some simple examples where we also can look at some code. So in this case, we have a function. So we just have two parameters we're optimizing, and our j is this nonlinear function of those parameters. So we need to first compute the partial derivatives in order to get the gradient. So let me ask, is Justin Scufa here? Okay, what about Brandon Gemperline? Okay, what about Connor Churin?
Yeah.
Okay, so how do we do the first one? What's dj dw1?
We just take derivative with respect to w1, so it would be 2w1 plus 2w1 w2 cubed, right? 2w cubed.
Yeah, we get rid of the w1.
Yeah.
Yeah. Yeah, make sure to review your basic calculus, because this shows up a lot in different problems, test problems and homework. Okay, yeah, that's what we got for the first one. And then the second one, let's see, is Daniel Kowalski here?
Yeah.
Okay, yeah, so what do we got for the second one?
6w1 w2 squared.
Right, 6w1 w2 squared. Okay, and then now that we have individually computed those partial derivatives, we can just stuff them into this gradient expression. And that's our gradient. So, so this code at the right, it creates a function that takes in our vector w. And usually we want to do two things simultaneously. We want to evaluate the value of the cost, because this is something we might want to monitor and see, is this thing actually decreasing? And then here we compute those partial derivatives, which are scalars, and then here we stuff them into a NumPy array, and then our function returns two things. It returns the cost and the gradient with respect to our parameters w. Okay, so that's a pretty simple example. Any questions on this? Okay, let's move on to a little bit more interesting one. So in this case, we have some targets. This is like a regression problem, so we have some targets yi. But rather than using a linear model, you can see we have a two-parameter exponential model. So we have an exponential where B controls the power of our model, and then A is like a linear scaling on it. So we would like to choose our A and B to get the best RSS for this exponential predictor. And there's actually many applications of this model. So what we can do in principle is we can, we'll learn that there's an algorithm gradient descent that we can use for this. And the first step is to figure out what are the gradients going to be. So, so what do we have for, let's see, is Nils Sommerfeld? Okay. Yeah, what do we got for DJ DA?
So 1/2 sum from 1 to n, everything into parentheses, and then times negative e to the minus pxi.
Okay, what about the 2?
Or, sorry,
Yeah.
2 and 1/2 will cancel.
Yeah, those are going to cancel, so I won't write the 1/2. Yep, and then, so yeah, like you said, we have to take the derivative of this with respect to B. And if you remember your calculus, there's going to be a minus, there's going to be A, E, and then there's going to be another B. Let's see, should have made room.
Shouldn't be the derivative with respect to a.
Oh, sorry, yes, you're right, we're doing with respect to A. So I was actually, let's just slide this over to the one below it. Okay, and that was a little bit harder than this one. So for this one, we have this. Okay, and then we just have E minus B xi. Does everybody agree? Did I make any mistakes? Okay, so this is what we have. So these are the things we want to compute, and here, we. Oh, did I? Oh, sorry. I did mess up. This actually should be xi. Okay, now we're good. Okay, so this code, now this wants to compute, once again, the cost, which is this, as well as the gradient. And when you write this kind of code, keep in mind that in a lot of modern applications, you're going to be doing this on maybe massive data sets, and maybe you have to run these gradient things like billions of times. So what you program is very important. You want to keep in mind computational complexity. And so when you see things like E, or sine or cosine, these computations are a lot more expensive than multiplies. They involve either lookup tables or different things to compute these transcendental functions than simple multiplies. So you want to make sure that you are not in your code doing this more times than you need. So what you want to do is you want to look for patterns. Like this thing is showing up here, 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 here. I don't want to recompute the same thing 5 times, right? I want to compute it once, store it, and then use it in a multiply. So here we are computing we're going to call it C, but it's going to be that term. And then you can see how we're using C here, and we're going to use it here, 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 C, C, and so on. And then we can actually even be a little bit more clever. We notice that this thing occurs 3 times. So let's also define that. That's what this y error is. So that, we'll compute that once and then use that several times. Okay. The other thing that we see going on is something called broadcasting. Although I wrote Python broadcasting, it really should be NumPy broadcasting. Broadcasting is a very natural thing that you guys, I think, have all seen before in the code, where Python or NumPy is smart about how it does multiplies with arrays and vectors. So for example, X is really going to be like a vector of data, right? But when we're doing this, B times X, NumPy is smart enough to take the scalar B and multiply it against every element in X. And then, let's see, C is going to be a vector. I'm looking for another example. Oh, okay, let's look at this. So Y_air is a vector, and here we're taking it to a power. We're squaring it. So NumPy is smart enough to square every element, right? Because there's no such thing, like if on a test you had a vector Y and you wrote squared, you would get points taken off because you can't square a vector. You can't square a vector in a linear algebra textbook or an exam or homework in this class. But in some sense, you can in NumPy because it's doing something specific. It's interpreting this as an element-wise square. And so that's something else that's happening. And here's another example of this, where we're multiplying a whole bunch of vectors times each other, and it's doing element-wise multiplies of X and Y_air and C. Those are all vectors. A is a scalar, but. So it's smart in how it does this. And we're going to see some even more interesting and smart ways of doing broadcasting going forward, but this is just, I think, the first time I'm kind of explicitly calling it out. Otherwise, I think everything here is pretty standard. I can't remember if you've seen this in labs. Have you generated random numbers? Okay, because this is something that happens pretty frequently. You just want to, test something or generate some random noise or something. So NumPy has different ways of generating random numbers, and this is the current way they want you to do it. Okay, great. So this is a good time to stop. We'll get into some more math next time. But any questions on the midterm coming up on Friday? Okay, so I posted the equation sheet. Hopefully there's no more typos in it. I kept finding typos. And I posted the extra practice problems. Okay, see you guys on Wednesday.